Hello and welcome to the MPLAB Mindi Analog Simulator live stream. I'm your host, Austin Caphammer, and I'm joined today by subject matter expert, MD Khan. Thank you for joining us today, MD.
Pleasure to be here.
Back in the booth, we have Theon and Josh joining us today. Thanks for helping us out.
Hi, Austin. Pleasure to be here. I am so excited to be simulating stuff on live stream today. I did not sleep last night.
Oh man, yeah, thanks for having us. I'm actually the opposite. I actually slept pretty well last night, so I'm feeling pretty good.
Also, we have in chat our colleague Edward Violescu, who will be answering questions in chat as we go through the live stream.
Hey, Eddie.
Awesome, cool. And Josh, it sounds like maybe we have some free demo boards back there?
Yes, I would love to talk about that. So this right here is the MCP 16311 and 12 evaluation board. It's a synchronous buck regulator. So we're actually going to be giving away 5 of these to 5 of the audience members who will be filling out a survey for us at the end of the live stream. So please be vigilant and pay attention, and that's going to come out at the end as well too. And we love to give away to you guys.
Josh, those are awesome boards.
They are fantastic.
That was way better than my plan to give away Austin's tie.
Oh my goodness, where'd you get that from?
Yeah, when did you get that, Theon? That's my question.
Always lock your desk, Austin.
Oh my goodness. Ties and desks.
Okay, and to our audience, feel free to leave comments below and send emails to livestream@microchip.com. We'll do our best to respond to those as soon as possible. So, MD, why should, what exactly is the MPLAB Mindi?
The MPLAB Mindi Analog Simulator is a powerful free tool that can be used for electronic circuit simulations. Microchip has built an ecosystem for analog and power design that spans from knowledge base that's ever growing to software and hardware tools. The Mindi simulator is a critical piece of this ecosystem.
Okay, and what's under the hood of the simulator?
Good question. I will be taking the audience through a couple of simulations today, so we will get a look at it firsthand. Before we dive into it, let me speak to that a little bit. The Mindi simulator actually is made up of 2 different engines, SIMetrix and SIMPLIS. SIMetrix is a classic SPICE engine that can be used for general mixed signal and analog designs. SIMPLIS, on the other hand, is more geared towards switch mode power supply designs. It uses piecewise linear models of switching circuits, which results in simulations being completed significantly faster compared to the classic SPICE engines.
Awesome, awesome. Well, thanks for explaining that to me, MD. And well, now that I understand it, do you think that, why should our audience be interested, I should ask?
That's actually a fascinating question. Electronic circuit design can be simplified through simulations. The Mindi simulator allows a user to model device and circuit behavior over a wide range of operating conditions, which can be used to replicate real-world challenges and without having to commit into designs in hardware. There are a lot of benefits in doing that. For instance, you won't have a graveyard of dead components in your lab, which I have. You can avoid that, and you can also use the Mindi simulator to essentially make sure that you're ready to move on to hardware design.
Okay, awesome. Well, so it sounds like it could be a great learning tool as well?
Yes, it's an excellent learning tool. The Mindi simulator can allow users to learn about switch mode power supply design by going through the different topologies and testing them out over corner cases and different operating conditions.
Awesome, cool. Well, it's definitely a useful tool for those that are involved in that design process, and it sounds like it expedites the time from concept to market?
Yes, most definitely.
Cool. Well, do you think that maybe we could see a simulation of that MCP 16311?
Yes, for sure.
Cool.
We can move on to the Mindi environment. I have the Mindi software running already. I'm on the welcome page. I'm gonna now search for the MCP 16311 here.
So MD, why the MCP 16311?
It's because the 16311 is a nifty, compact step-down converter. And my colleague Bogdan ran a case study where he compared the results from the lab bench to the Mindi simulations. The real reason for that is to provide the users with evidence that should gain some confidence in their communities so that they can start with the Mindi simulator, complete their designs over there, and then move on to the hardware design.
Okay.
So today we're going to look at the synchronous buck example. It comes preloaded with the Mindi simulator. I'm going to do a zoom to fit so to provide better visuals here. This is a relatively simple buck converter where we have 7 volts in, 5 volts out. The simulation is actually already set up. So all we need to do is just hit run and it will give us some results and we can speak to that. So shall we take a crack at it?
Yeah, let's take a look. Seems to have ran pretty quickly.
It did. Remember I pointed out how the SIMPLIS environment can be significantly faster. So we have some evidence of it here.
Okay.
So why don't I undock here to see these curves.
And how does this compare to like an online tool?
That is a very interesting question. Online tools have their place as well. At the moment for Microchip devices, the Mindi simulator is the right tool because we do provide a local installation. So right now my computer is the only thing that determines how well Mindi is performing over here.
Got it.
The Mindi simulator is not reliant on the internet connection or the server connections that you're dealing with.
Okay.
We were looking at really 2 things on the output, I out and V out. But as you can see, we can only have one thing on the screen. This is not a mistake. What we need to do is to stack the curves.
Oh, okay.
So now we do have the targeted 5 volts out.
Okay.
So let's take a look at something else here. See how there's a bit of a delay from when we first started to when we hit the 5 volts?
Mm-hmm.
Do we have a question?
Chat was asking if this simulator will support models from other sources, if they could get models from other places and import them into the MPLAB Mindi tool.
Some of them most definitely will. However, because of the wide variety of models available, I'm not able to guarantee which ones will, which one won't. You can try and bring them into the tool, and a lot of times it will just work as soon as you drop it in.
Thank you, MD. Appreciate it.
Sure. So getting back to the screen here, excuse me, we have the simulation results. We have the 5 volts that we needed. Now, it did take a few microseconds to get to that value. So let's see how long it takes from when the 16311 is first enabled to get to that target voltage.
Okay.
To do that, I'm going to place a probe here, a voltage probe.
And what's the significance of the measurement you're about to show me here, MD?
That's a very good question. This is telling us how long it takes for our circuit to be up and running. So I'm going to stack it here before I get into that question. So let's measure this value and then we'll come back to that.
Okay.
To measure it, we can use the same principles as you would in an oscilloscope. You can go to your cursors, you can pull them up right here, or you can press C on your keyboard. Got 2 cursors going, so let's find out. I'm just holding it with the mouse and grabbing it to move on to the right values. On the output, I'm going to 90%.
Okay.
That's reasonable enough, close to 4.5. So about 294 microseconds. So it took us that amount of time from when we first enabled the device to get to that value. This is important because if you have a critical system that needs to be up and running within a certain amount of time, you want to know how long it takes for this power supply to stabilize, right? So that's the point here.
Okay.
You hear a question from the booth?
Fabian was asking if we can create models for ideal or perfect devices and incorporate those into our simulations.
You could. It gives the users the flexibility to work with all sorts of models. Microchip does provide models that will allow the users to replicate real world conditions. So if you would like to get your own models, you definitely have the freedom to do that. Now we're going back to the screen for the simulation. Now, we started with 7 volts, we got 5 volts out. Mission accomplished. However, if we had a different input voltage, what would happen then? That's what we need to find out. If you don't always have the 7 volts available, let's say you had a different input voltage available.
Okay.
So give me a value that I can put in here. What do you think?
Let's double it.
Okay. So we're at 7 volts. I'm gonna change it here to 14, and let's run this. Fingers crossed.
Once again, ran pretty quickly.
It did.
We're
So
not-
I'm gonna undock it again.
Okay, and we'll stack it to.
Yes. See, you're already catching on.
Oh, there you go.
Now remember, we were saying we need the 5 volts out, even though the input doubled. Guess what? We still have the 5 volts out.
Okay.
This is critical.
And why is that so important?
Imagine on the output of this MCP16311, you connected a PIC microcontroller or a DS PIC, which can only take up to 5.5 volts. If your input changed and your output wasn't able to regulate it, guess what would happen? You would destroy the device on the other end.
Yeah, we don't want
So
that.
you want, yeah, exactly. So you want to be providing a regulated, stable voltage. That's the job of this device, and we can see how it can do it through the simulations.
Awesome.
Do you have a question?
Yes, we do have a question. This is from the booth, actually. So we're giving the giveaway at the end of the live stream as well, too. But then, just in case that someone's not able to get it, how would they get an eval board?
The eval board can be found through Microchip.com. If you go to the product page, there's actually some literature as well that you can use to get some knowledge-based articles and app notes. And the eval board can be found through there or through Microchip Direct.
I gotcha. Thank you, MD.
Awesome. And to our audience, we will have some web links available underneath the video. And speaking of our audience, MD, do you think we could run another simulation for them?
Sure. This time, let's take a look at transient load step. So I'm going to go through the Mindi environment, the Mindi simulator environment again. So we're going to pick AC transient load step. I'm going to do a fit to get a better visual here. This is also set up for us. The schematic is ready and the simulation as well. I want to point out a couple of things that we'll come back to. You see there's a Bode analyzer. This is going to give us some interesting results that we can discuss.
Okay.
So let's run it and see what happens. Pretty quick.
And this is when the undocking and the stacking comes into play again?
Yes.
All right.
Yes. Do we have a question?
We do. So we know this is our analog simulation tool, but one of our users was asking if it can simulate any sort of digital interfaces or the interconnects between digital interfaces.
It can. It depends on the setup. There's so much variability. It will depend on how you set it up.
Thank you, MD. Appreciate it.
Sure. We're getting back to the curves now. So once again, as Austin pointed out, always stack them. So we have an interesting phenomenon here. We have the I out, which is the load. It went up, and as a result, our voltage, which was our stable 5 volts, is actually getting some undershoot.
Yeah, we can see it kind of reflect there.
Yes, absolutely. And on the other end, when the load is coming down, you see a little bit of an overshoot, and even worse, you see some settling time here. This is not a problem. This is just how this topology is going to work. What we need to do is, the designers need to be aware of what this overshoot and undershoot is and what the settling time is. Being aware of it allows them to make the decision whether this is the right device for their design. That's really the point of this part.
Awesome.
Now, we did show a Bode analyzer, so let's see what we have here. We've got gain and phase plots. Usually when we work with these plots, we want to know the stability of the system. So we look at the gain and phase margins.
Okay.
So let's measure these. We can either use the cursors to measure manually, but I like to use the measurement tool. If you go up here to measure, and we go to more functions, because the initial list did not have what we're looking for. We scroll down here. You can see that we have the gain crossover frequency. So let's take a look at that first. We'll do a quick spot check. You have to select the right curve. So in this case, it would be the gain curve. We have about 14.2 kilohertz, right? So if we follow the gain curve, which in this case is green, When it goes through 0 dB, we're at about 14.2.
Very close.
Yep. Now let's go back and take the gain and phase measurements. Same thing, you can also measure max and min and frequencies. So gain margin, select the right curve, 28.9.
Very close again.
Now the last one would be our phase margin. This time we select phase, and we got 41.6 degrees.
Okay, and why would our audience care to measure these values?
It's a great question. In terms of power supply design, the frequency response tells us how the energy of the system is spread out throughout the range, the frequency range. This is very important to understand about the stability of the design. If a design is not stable, really bad things could happen.
Yeah, absolutely. Well, are there any tools for this sort of analysis and adjustments?
Yes, I can get into it. We can get back to Mindi and we can take a look at it. Do we have a question?
We have two questions in the chat. The first one was about our tools for simulating MCU code. Now, we have a different set of IDE environments for the simulation of the microcontroller code, but is there any way to relate that to this analog simulation?
At the moment, I don't believe there is, but you can definitely replicate what you're trying to do in the Mindi simulator environment as well.
Okay. And second question, MD, what are the limitations on this tool compared to the commercial version of SIMetrix that's available from that vendor?
That's a great question and a tough one. I can tell you that for Microchip devices, the Mindi simulator will get you everything that you need. The commercial versions of SIMPLIS and SIMetrix does come with a lot of extra capabilities. Right now, we don't need to use them for what we're going through.
Thank you, MD. Appreciate it.
Sure. So you asked about the design analyzer.
Yeah,
So let's take a look at that, and we can have another discussion on that topic. So we go back to the welcome page once again, the 16311. This time we can pick the design analyzer from here. Schematic kind of looks similar to what we've worked with so far, doesn't it?
Mm-hmm.
All right. So in this case, E represents the input voltage, U represents the output voltage. So we got 30 and 12. But hang on, there's a couple other tabs, right? What is this analyzer doing for us? That's probably what everybody's wondering. Mm-hmm. So if you go to the System tab, it tells you how big your inductor needs to be. So the default for the values we're working with is 56 microhenry. They also provide some capacitor values. And then if we move to the compensation section, it gives us the ratios of our top and our bottom, which feeds into the feedback.
Okay.
This is important because what happens if you change your input and output voltages? That's the biggest benefit of using the analyzer. Mm-hmm. So let's make it 12 and 3/3.
And will the analyzer automatically adjust in these values, or?
Well, let's find out.
Okay.
So it does say that suggested values have changed.
Okay.
So we didn't get a look at that before, but now look. Mm-hmm. It's 56, but the suggested value is 15. It actually does make sense too. You've reduced the voltages you're working with, so you maybe don't need a big bulky inductor. Mm-hmm. And this is key because then you're not over designing the system either. So let's change these values to what the suggested ones are, and then we can run another simulation because that's what we like to do. And then we'll see what the results are.
Let's check it out.
All righty, I'm just going to quickly plug this in. This can stay the same. Our top's 36. Bottom's 11.5. And let's load the schematic. So you see, the default values actually have changed. So that means what we did with the analyzer did update on the schematic as well. So let's give it a spin, see if we can actually get the 3.3 volts out.
Yeah. And undocking and stacking again.
Yes. So we're not going to get into the second curve today.
Okay.
So we're just going to take a look at that output so that we can prove that the design analyzer did, in fact, lead us to the right path. See right here, the output, it did give us the value we're looking for.
Perfect. Well, and could you give us an example? Am I able to choose a component with the Mindi simulator? Is that an additional benefit?
Sure, we will get into that discussion.
Okay.
I believe the booth had a question.
We do. Now, one of our viewers was asking about the temperature simulations or real-world condition simulation capabilities of the tool, and I think I heard a rumor that the MPLAB Mindi simulator will actually do Monte Carlo analysis for you,
Yes, that's correct. It will.
including the temperature capabilities.
Yes, I have had some simulations where we have simulated under, for instance, 3 different temperature ranges.
Thank you, MD. Sorry
Sure.
for the interruption.
That's okay. So now let's jump back into the Mindi environment one more time. This is a bigger question that we're trying to answer. You asked, can we make a component selection? That's what this is about, right? You've made a design, now you want to know, did I pick the right device? Is the MCP16311 the right device? So we'll do a quick exercise, and there we can kind of see some nuances on making that decision.
Cool. Excited to see it.
Sure. All right, let's load up the 16311 one more time. This time we're going to reload the AC transient load step. Going to fit right here. I actually don't need the Bode analyzer, so I'm going to delete this. Just click and press delete on the keyboard. It'll clean it up.
Pretty user-friendly.
Very user-friendly. So what we're trying to do right now is show to the users, as the load changes from a light load to a larger one, what happens to that output? How does the Vout respond? And keep an eye out for this. So I'm going to connect it right here. And the resistor value, I am actually going to change it so that I can exaggerate this impact.
Okay.
As you can see, it used to be voltage divided by current. Now we're going to just type in the value directly. So let's do 500 here. And on the load side, because this is a different test, I'm going to actually provide a sawtooth. And I'm going to change the period to, let's make it 10. And in terms of the pulse, I'm going to make it 200. This should update the offset and amplitude. Now, the last thing we need to do before we run off is that we need to check if our simulation settings are going to match up with what we just did. Remember, we just made it almost 10 times the load step over there. So let's go back to simulator, choose analysis. We actually are not interested in AC or pop this time. Let's go to the transient section. See, it was only 1.4 milliseconds.
Okay.
So it would not have captured what we were looking for. So we need to at least give it 10.
Okay. A little bit of a larger window there.
Oh, yeah.
Okay.
Shall we run it?
Yeah.
All right. Let's take a look at this here. Uh-oh, what's going on? You see what's going on that output right now? It's no longer a stable, happy 5 volts anymore.
Okay.
So don't worry, though. I have a plan.
Okay.
We'll show.
Does
what's
it
going
involve
on.
undocking and then stacking the...
Yes, that does. All right, so let's take a closer look at this thing. So remember I told you how do we make that component selection? So what I want to focus on right now is this curve that we have in front of us. But before we do that, let's stay true to our principles. As this load changes, see there's a transition point. Up until that point, under light load conditions, you see this ripple on that Vout? This could freak people out. So we want to make sure that in your design, can you handle this ripple? Is that okay? And that's the design decision that we're trying to make here. If you want to know if the MCP16311 was the right choice, you need to obviously read the data sheet, but you want to find out right here where the ripple is higher, it's actually in PFM mode.
Okay.
And once the load reaches a certain point, and it also depends on the ratio of the input and output voltages. Once it goes to a higher value on the load, you see that it transitions to a PWM mode, which is very nice and quiet.
Yeah, settles out a little bit there.
Yes. So you might be wondering, well, why did we offer the PFM mode? Well, that's because if you want to do a trade-off between efficiency and ripple, then if you can handle this ripple, the PFM PWM transition allows you probably a more efficient design. However, if you are someone who's thinking, I don't care about that extra efficiency, I want a clean V out throughout the different ranges on the load, then move to the 16312.
Okay.
So that's the design decision. That's how the Mindi simulator can help somebody to make that decision. Do we have a question?
Yeah, we do. A couple kind of related questions came up in chat. The first one was about moving from that suggested passive component value to an actual real component. Does this tool have models for actual vendor passive components in it?
In some cases we do. I'm not sure if we can comment on having all the things that people are working with, but we do have a pretty comprehensive library.
And then once we start working with actual real-world passive components, those components have tolerances.
Yes.
Are we able to compensate for the component tolerances in the simulation to figure out what it would do over the entire distribution of passive components we'd get in production?
Man, you're throwing all these tough questions at me.
I'm just telling you what the chat asked.
So we
Don't blame me.
We can actually take that into account. If you look at the models that are available, these are not simple models. A lot of times these are fairly detailed. So the question about tolerances, how it does over temperature, it is taken into account and to a very, very minute detail in most cases.
Thanks, MD. Appreciate the answers. I will scour chat for a softball question for you. And I'll let you know when I find one.
I really appreciate it.
Well, MD, after showing me the component selection benefit as well, it definitely sounds like the moral of the story is that there is help available at different stages of the design for Microchip customers and people who are interested in using Mindi, the Mindi simulator. The simulator does fit well within Microchip's business model and providing that support for a range of customers. So thank you for taking the time to show that to me.
Sure. Do we have another question?
Yes, this is a question from the booth actually. So for our audience, I'm just wondering how often does MPLAB Mindi Analog Simulator get updated in a year? And then when can we expect the next update as well too? Could you comment on that?
Sure. We have about 3 major updates that are spread out throughout the year. And then in between, we'll have smaller releases that can be found in the software library section of the MPLAB Mindi webpage.
All right, thank you, MD. And also one more question though. So if one of our customers was looking to try and request a new device model for MPLAB Mindi, where would they go to try and do that? How would they try to reach out for that?
They just started with the tool. They're already unhappy with what's available. I'm just kidding. They can go to our support network, which is through cases. They can turn in a support case. We also have a power check tool, which can be used to review designs. So that was the other thing I was going to talk to you about, Austin. You mentioned the ecosystem that we provide for analog and power designs. We also provide support as well. If you need our opinion on something, you can go through our support cases or the power check tool as well.
Awesome.
Great, thank you
Thanks,
so much.
MD.
Sure.
Well, and I know I'm sure there's a lot of viewers out there that would like a little bit more info. Do you know if there's any additional Mindi training available?
Yes, there is. You can go to the same place that I went to prepare for this live stream. So I'm going to show you through the Mindi environment. Always go to the MPLAB Mindi environment and we can go to Getting Help right here on the web page. The hands-on workbook, that's what I used. So let's take a look at that. If you're wondering what the other tab was, this was the MPLAB Mindi Analog Simulator page.
Okay.
What have we here?
Theon playing the guitar.
He wishes. So right now we have about 15 chapters that are suitable for users of all different skill levels. In fact, if our audience paid attention and they go back and try chapter 4, I think they'll find it very interesting.
Okay.
I took some of those examples from there.
All right.
And we also have other training here as well through Microchip Developer.
Cool. Well, in addition to the Mindi webpage, the links will also be provided in the description here of the video, along with the Mindi software download. And before we go, did we have any last-minute questions from the audience?
Yes. Do you have any advice on moving from the simulation to an actual board layout, or how one of our customers could go about doing that?
That's an interesting question. So you want to first simulate your design and make sure the design is robust. And to move on to actual hardware design, you would go about designing the board, making that schematic, and then laying it out. We have a lot of literature available in terms of how to do the layout. For instance, if you're working with a driver, don't place the device with really long traces because the extra inductance could be a problem. We have a lot of these tips and tricks that we've learned over the years available in app notes and tech briefs.
One of our customers was asking about antenna traces specifically. Do we have any layout services that might help them with that, independent of MPLAB Mindi analog simulator?
Well, as I was mentioning, the PowerCheck is a very good option for reviewing designs, and I would recommend that you take a look at that.
Thank you, MD. I think we'll try to get a link for PowerCheck into the chat as well if anyone wants to check out that service.
Awesome. And to our audience, feel free, once again, just to send those emails to livestream@microchip.com if we weren't able to answer your question. We appreciate you listening in today about the MPLAB Mindi Analog Simulator so much. I'd also like to say thank you to our subject matter expert, MD.
Pleasure to be here.
And also thank you to Fion and Josh in the booth.
Absolutely.
Austin, MD, it's been a lot of fun. Really enjoy watching simulations in action. Would also like to thank Edward in chat, who is helping answer questions as we go, and the stage crew here at Microchip that helped make this happen. Put together a fantastic live
That's
stream.
everything we dreamed of last night, right? Absolutely.
I wasn't dreaming. I was awake.
You're right. It was just me. Also, before, while the camera's still on us, wanted to do one last reminder as well for the giveaway. So just in a few moments, actually, we'll be dropping the link off for the survey inside the chat. And then, so from that, again, the first 5 people to fill out that survey will be getting one of the MCP 16, 3, 11, and 12 evaluation boards. You know, MD just talks so much into it right now. I'm pretty sure you guys are like, oh, I got to have that right now, too. So as soon as that link pops up, please be sure to go fill it out for us. It helps us out a lot as well, too. And you guys will also get one of these, too. So thank you.
Awesome. Well, once again, thank you all for sticking around until the end of the live stream and joining us today. And now, enjoy our post-credit scene.
I'm excited for it.
Hey, so I finished my new PCB design.
Great! Let's test it out!
Oh no.
An error message! Oh, look, more error messages!
Oh.
Congratulations for designing an exquisite piece of garbage! Oh, I have to ask.
No,
did
don't
you say-
ask. No, 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 no,
Will
no,
you
no,
stop
no,
it?
no.
Did you simulate that?
No. Only in my mind.